Hello and welcome back to Compiler Programming. Today I want to talk about structs and functions. So obviously right now language has function implementation and it has this very basic struct support. And one of the reasons I didn't really invest much into working on structs is because I wasn't exactly sure how I want them to work. The thing is, you have structs, you have unions, you have tagged unions that are sort of the same. And then you also have functions, which are sort of the same if you consider that functions should have like named arguments and you should be able to call a function by specifying like argument name and then the value and not in the order that they were defined. Then you also have arrays, which I don't really have right now. And I mean, I sort of have them, but not really. And they are sort of variants of this struct that also have weird properties. So I really wanted to figure out if there is some sort of more universal way to represent this kind of thing. And I think I figured out what it should be. So today, first, I want to talk about the idea that I have, and then we will try to start implementing. I'm not sure how much we'll be able to do today, but at least I will start working on it. So to understand what is happening, let me try to draw a bit of stuff. So first of all, we have a struct, right? So what is a struct? Well, if we look at it in the memory, then a struct is essentially just a piece of, a kind of a part of memory. And I can't draw straight lines for my life in this program, but whatever. So we have some memory, and if we have a struct that looks like, I don't know, int a, and then int b, then we would have, make the brush smaller. So this will be the start of the struct, right? So we'll have some kind of pointer. So my struct, which is like a variable. And even if it is not a pointer, and then it just means that it points to a struct, points to a stack. But let's consider that we have like this my struct pointer, and that just points to some memory address that is over here. And if we look at, we have like two fields, int a and int b. I'm ignoring padding for now. I actually talked through the padding in one of the previous videos, so I'm not gonna talk about this. But if we say that this each square is 1 byte, then so this part, apparently I really can't draw. Okay, let me grab also different color just so it's more visible. So we'll have till here, I guess. Oops. Like this. This is going to be A, right? And this is going to be B. So let's say we have my struct X. So when you say X A, that literally just means take the address of X and add 0 to it, because this is the first field, right? And if we say X B, that means it's X plus 4. So this is what struct is. And I mean, you can have fields of different sizes, right? But essentially just the field just specifies an offset into the memory that the struct occupies. Okay, so that is structs. And maybe I can zoom out a bit. And now let's assume that we have arrays. So array, well, array is sort of exactly the same thing, right? And in fact, if you have a struct with two items that are exactly the same, then I will not even like draw. So in fact, this exactly the same struct can also be said that it's int a2, right? This is exactly the same thing. And I can say again a0, which is going to be just a, and then if it's a1, that is just a plus 4. So it is sort of exactly the same math. The only difference between structs and arrays that in arrays is you must have uniform um, members, and in struct you can have non-uniform one, but and also in array you kind of don't have names for them. You just use indexes for referring to each of the items. Okay, so I mean, I think most of you can agree that structs and arrays are the same, more or less. But now it is a bit more tricky, because what I want to talk about now is I want to talk about functions, or more precisely, function calls. Function call. Actually, function body as well. So what's that about? Okay, so imagine I do some kind of function, and it is int a and int b. And I don't care about what the return type is, so let's just say void return type, and I don't care what the body of it is right now. So this is the definition of the function, and then we do function of, I don't know, 40 and 2, right? So maybe let me move this a bit up. Function 42. Okay, so we are calling this function. What does it actually do? Well, function has a colon convention that says that where each of the arguments is supposed to be put into. So in Windows calling convention, or Windows 64-bit to be precise, because 32-bit had a very different calling convention. But for 64-bit, you would put the first argument in RCX and the second argument in RDX if they fit into those into the size of the registers. Now integers do fit into the size of the registers, so that means that we essentially just have like, yeah, we will say RCX is 40 and RDX is whatever, 2. Okay, these are two argument functions. But there are also situations where functions are actually, like, if you have more than 4 arguments on x86 64 in Windows, then you start to put them on the stack. And this is where interesting things begin. So let me do a bit more here. So we have int a, int b, int c, int d, and we would say int e. Actually, we'll call it stack or whatever. Let's call it. Okay, now we have this function. So first 4 arguments are not interesting, but this argument in a function actually goes onto the stack, and then in here you would get an address of the place where actually, yeah, it just goes in the stack. And the function knows where to look it up. So when the body of the function wants to do something with e, so let's just say we have like return e as the body of this function. So what that means is that we would have something like return in pseudocode would be RSP, which is the register for the stack, and then there is like plus blah 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 that is internal to the function. I don't want to go into what that is, and then plus 0. And 0 is just specifies an offset of e. Like if we had another one, it would be int cd ef f. So then it would be like plus 4 if it would be f here. The point I'm trying to make here is that for the function case, after a certain number of arguments, we start to have this same situation as we have for structs, where we have this base address, which is this part, and then each argument is just put at some kind of offset from that address. And this is an interesting sort of observation. Now, if we want, we can try to describe the sort of the calling convention in a struct-like way, where we say that, okay, I don't know, arg, or we say a, right? Int a, and then I would say that we have an extra field in a struct descriptor that would say, or in something descriptor that would say where it goes. So say a, it's rcx. Then we have, I will not repeat, int. So this is rdx, this is r8, this is r9, and this is now what? Well, if we introduce a concept of like also a base address, and we put this RSP into this base address, so this would be the base address, then our E here becomes base plus 0. And we can pretty easily represent that. Okay, so if we look at this format, it looks like we can represent what we need for the functions, which is pretty neat. What about structs? Well, again, we have the base address, right? So this is the base address here. And then we have offsets. So the only difference with structs is that they always have these addresses relative to the base, and they cannot in C definition refer to registers, but technically there is no reason why they couldn't refer to registers. It's just an arbitrary limitations that C decided to put in, and everybody else followed it. I mean, this is a bit connected to the optimization paths that is happening in the compiler and how registers are assigned, but conceptually, there is sort of no reason why it has to be limited to just a base address for the struct. It can be anything. Like you can imagine that we have some kind of a layout. I want to call this memory layout that will just, for example, say that base address is some, 1, 2, 3, whatever. Like it's a fixed address. Or this is a fixed address, or whatever else. Like why not have a struct or like a layout that you can work in a uniform way, and it's just that when you access this particular field, you will be accessing something static. Maybe it's an address, maybe it's a completely static value, and I think this might end up being good. It might end up being terrible, but I still want to try to make this happen because this feels to me like this is an abstraction that can unify this stuff and just make my life slightly simpler, and also give very powerful tools to the developers, because they could implement something like libffi without really assembly, with just specifying this kind of stuff. And there are interesting use cases that I think can happen. But the point is that you can do whatever you want. Another thing, for example, that would be interesting is if you ever worked with something like STB array, um, then the idea there is it's a like C library for arrays, for dynamic arrays, and when you store an array, you point to base address, but then if you want to know the size of that array, that size is actually stored at base minus 8. So this is something that is not representable right now at all in any of the languages that I know. You can't say that actually look at that place behind me. So that's something also that would be possible. One final thing that is sort of interesting here is that if I have this working, then I also would automatically get zero cost destructuring for assignments. So if I write something like int, I think I will use square braces for this. So I'll say int ab is, I don't know, uh, my struct, star my struct, I guess. Then this is pretty straightforward, right? We create two variables on the stack. So we say that this is like RSP plus whatever, and then this would be plus 0, this is plus 4, and then I just copy over, or I might decide to assign this to, I don't know, RAX or whatever register I want, right? So this is very neat, and this is something that is very painful to implement otherwise, I think, and something I need to implement anyway. So this is roughly the plan, and then we will see where it goes from there. I hope it makes sense. If you didn't understand something, please feel free to add a comment in the video below. I'll be happy to answer and explain. But for now, let's try to actually make at least some of these happen. And there are two places I could start with. I could start with structs, or I could start with functions. I think I will try to start with functions, and then we will see where that goes. This also is helpful for the functions because right now, if we look at the function, ensure compiled function body, right. So there is this function called function argument value at index that is defined, I guess, in here. Yeah. That is a code version of the layout I was saying. So see, you have like register C, D, R8, and R9, and it's exactly the register that I was talking about, but this is done in code. And if I want also the compiler to be available on different platforms, doing it in code is not the most flexible way, and also it will be quite annoying for people to implement if they want to port this to some new platform. So let's try to figure out if we can do something better. And I guess we will start by marking this, that we will need to work on this, and we will go to generate types and just try to figure out what is going to be the type of that memory layout thing I wanted to have. So we already have descriptors for struct fields, and this is going to be somewhat similar. So let's just try to figure this out. So struct I'm just wondering if I want to make it a descriptor right away or not. I guess doesn't matter. Let's start just like this. Memory layout. What is a memory layout? Well, it is the same as with structs. We don't want to have name, we more want to say that there is storage. And we would say that this is going to be base. And this is going to hold address of the base for relative fields. This base might be none. It's perfectly fine as long as there are no fields that try to refer to the base. We don't need one. But if we do have fields that refer to the base, and we would expect to have that working. So we would say memory layout. So this is array memory layout. I don't know if I should call it field. I guess item is fine. And then we would have items. And then we have memory layout item here. Okay, what is a memory layout item? Well, it has a name. Then it has, we need to say whether it is relative to the base or not. So let's create, I need a union here, I guess. So let's copy this union. Something like that. And we would say memory layout item storage. And we would have to say one of them is base relative. Base relative. And the other one would be absolute. Okay. So we have absolute, we have base relative, and in both cases they are sort of, we still need to have the storage itself. I guess in absolute case we would have like just a regular storage, and then in here we would just have S64 offset. Okay. So now we need to put in here storage. No, that is the wrong way to do it. It should be like this. Storage, or I think I will not create the wrapper. Instead, I will structure it something like this. What does it look like? I need to put it here. So basically, I'm saying that part of the fields are gonna be the same, and part of the fields are gonna be different in this struct. And what I'm doing here is it's the meta program that generates the types, and also it generates the definitions for the types in the mass languages as well. So we can use them sort of across the compiler and the runtime. Okay, so we do have a name, and then we have either absolute or base relative. That sounds pretty good. Let's see if I have messed this up. Descriptor, array, memory layout, item, undeclared identifier. That is strange. Do I not create um, square array memory layout item pointer? There is a pointer, but there is no regular one. And that is because I don't know the sizes, right? Okay, where is it? Yeah. Yeah. We are generating them here, and here, and here, and here. Well, I mean, for now, I'll just cheat. I don't think it will actually fail now. Yeah, we don't actually have these descriptors, but that's fine. Okay, so that takes care of the type itself. Now we need to store it somewhere and start filling it in uh, as we deal with the function. Well, if we deal with the function, then let's store it on the function, I guess. Function argument, function return, function info. Okay, so we have arguments. Eventually we will replace it with the memory layout, but I don't want to break the program. So I will first just put it here, and we will go from there. Okay, let's find where we are creating the arguments. Great, so this is the creation of arguments, and we can also create a memory layout here. Array memory layout item capacity, that is fine. We actually do know the exact capacity that we want, I guess. No, not really, right? We need to go through this to figure out capacity. Well, whatever, and that is okay. So layout, that is items, and maybe let's be explicit and say that our base. Okay, what is our base? That is an interesting question. It depends on if we are looking on the function from the outside or from the inside. So it is possible that we would actually need two layouts, one for accepting arguments and one for the body. And the reason I'm saying that is because when you're calling a function, the stack pointer changes. So all the offsets will shift. I don't know. Let's not worry about that for just now, but I will get back to it in a moment. So I will just say 0 and add a fix me, provide stack location for arguments. We're just gonna take it one step at a time. Okay. So this is the layout. We created the items. We are going through the arguments and we are doing stuff. Now we will also do another thing with an argument. So we'll say dynamic array push of memory layout item. So that will be like this, and we are pushing it to here, items, we'll have a tag, and the tag for now, let's just say that this is going to be all tag absolute, and then we would have absolute. Can probably do it like this. Storage is well, here we can actually call this function that I mentioned, because it will provide us with the right stuff. Hmm. Do I want to do it that way, or do I want to do something better? Well, let's just think about that. So I could introduce index is 0, and then I would say storage argument storage. Well, let's start with it being empty and switch off index. Argument index. Right, it also needs to take care of the return descriptor. Windows calling conventions is not the greatest, let's just put it that way. It's very awkward to work with, but well, let's just call this function. It's fine. It's not going to be the fastest, but I will clean this up later. So what we will do is we will say value star argument value is this, right? Body context, we will say arg context, function is, I guess, this stuff. Index is going to be dynamic array length. Well, let's just introduce the index after all. Then I can probably move this into here, and then plus plus index. Okay, that means that we can use index and mode, let's say call, and we can put arg value storage. Okay, probably made a ton of mistakes, so let's see what is, if there are any problems. That's not tab, that should be tag. Okay, we are building. Let's just quickly check that we are not crashing. Didn't really do anything, but it never hurts to check. And apparently we did crash. And the reason we crashed is because we don't have the return descriptor. Okay, and I think here it makes sense to flip this around. Hopefully that will work. That's why I do this test. Okay, we are good. We are building. Everything is great. Let's set it to git index and we can continue working on this. Okay, so now comes the tricky part, because right now we are just always saying that this is an absolute layout. But what we could do, let me quickly think about it. In which order do I want to do it, and what do I want to finish up today? I guess one thing I can do right now is I can try to use this layout in a place where I would previously call this function, and then try to go from there. There is one thing that is actually missing here, and so I have memory layout base, and I have this memory layout item. Mm, it's also missing a descriptor, so that should be like so. And then absolute storage. So we can say descriptor is arg. Actually, it is descriptor. Where are you? Which argument? So I guess it's arg descriptor, and name is arg name, something like that. And does that work? Okay, so we have these things now, which is great. Do we still need function arguments then? Kind of. So if we move default expressions to memory layout, which might not actually be a bad idea, then that would work. There are some questions about scope rules when we will be doing that. But I guess we could. Yeah, let's just do it. So that's what I'm gonna do today. I'm gonna replace function arguments with memory layout. This is gonna be the thing. Okay, source range goes into here, and then default expression goes into here. And function argument is out. And you're also out. And we will get a lot of problems when we will be doing that. But we can tackle them one at a time. This thing does not know what to return, so we need to change item. Okay, memory layout item, name is okay, and descriptor, that's fine. We need to say tag is tag absolute, I guess. And for the storage, Well, for now, I will do it later on, even though it's gonna be a bit awkward. So, memory layout item, arg, that's fine. We would do a push. So we'll do this here. We would say that arg um, storage. Oh, let's just say arg absolute storage is arg value storage. And there's definitely stuff to clean up here, but for now that will do just fine. That needs to be a dot. Okay. We don't need to create this, I guess. Yeah, this is not a thing anymore. Okay. Right. Now we go over the arguments. Memory, layout, items. That is going to be a memory layout item, arg. That seems good. Reserve stack. Parse expression. I'm just trying to figure out where do we call this great function. No. I want memory layout item and layout items. Okay, we are not using it here, which is interesting. I guess there is other stuff. All right, because it's not internal, it's just index. So we call it here now, and we also call it when we call it. Yes, great. So the goal would be to get rid of this call now and instead just rely on the layout to figure out where to put this stuff. So let's get to that. Memory layout item, that is good. Items, target definition. Okay, I'm not gonna do that. Then we'll see what breaks. Okay. Right, we don't have the target argument. Let's create a fake one. Fake target arg is the following. So that would be descriptor is target arg definition descriptor. Then we have storage. So here for now, let's assert that target definition tag is memory layout item tag absolute. and say to do. Okay. A definition descriptor, absolute storage. And we even have a source range, so we can do source range is really the same stuff. Source. Maybe I should just put the value in there. Who knows? Fake target arc. So we are assigning to this. You're assigning to this. And here we will have fake dark source range, I guess. Yeah, I can't really make it on stack, so let's do it like this. Value make of context, and then we have descriptor, right? Descriptor, storage, all the same jazz as we did just now, just without names. Something like that. Does that work? Okay. And it's no longer sort of fake. Let's just call it target arc source range. Okay, I think we are making slow but steady progress. This is pretty easy. We can just replace arguments with memory layout. And here is right. So here we need to init it to be that. Then this also needs to be a memory layout. Right. So that is fine. Name, descriptor. Oh. That is a bit awkward and it will definitely break pretty badly if I don't fix this stuff. So what should I do about that? Well, let's leave it for a second. Yeah, that's fine. As long as there is an error here, I don't mind that. Let's go back here. And here we want to check layout items. Okay. Who else is angry at me? Looks like just this stuff. No, that was wrong. Okay. That takes care of that. Okay, I think the only thing we have is this stuff, which is uh, so I'm defining these compile time functions, which essentially is the same as what is happening in here. So this stuff, but I just have to do it again, I guess. Well, I definitely need to clean up, fix me, unify this with the compile time functions below. Okay, let's take that and see what we can do about that. So arguments, function arguments, so memory layout items, and here you would say arguments, that's fine. So the trick is here we need to do something else. So tag is tag absolute. Source range we don't have one. Name we have. Descriptor we have. And storage is what is problematic. So let's paste all of this stuff. And I guess. Oh, this thing also doesn't have a context. Oh, this is awkward. Awkward, awkward, awkward. Can I make this work somehow? I guess. This is going into quite a bit more refactoring than I would like, but I guess we have to do that. So the problem is we don't have a context at the point where we define those compile time functions. I'm just gonna remove that. And I would say storage for index. And okay, we're gonna keep the mode. We're gonna keep the function now. Instead of the function, we will just say argument index, argument index. I guess we will try to pass a descriptor here. If we can pull that off, that will be good. Source range we don't need. Byte size we will have. Function returns descriptor. So unfortunately, it does look like we need to have the function. Okay, we will pass it to you as well. That's great. Storage, register for descriptor. Return storage to value. Yep, you need to be storage now. Okay, that actually simplifies some stuff. And value make internal. Yeah, we don't need any of that. We can just return storage, I guess. And that would be return stack. Okay, so we have now a version of this that does not need to be a value, which is great. So first of all, we can do this type of jazz now. So make this a wrapper around the other one. Okay. Call this, and we're gonna say that storage is this, and we're gonna pass it. Yeah, I don't want the context. That was kind of the whole point of this. We would pass in function, we would pass in arg descriptor, we would pass argument index, and I guess I also need to pass in the mode. Okay. So that should take care of all of that. Okay, that looks actually good. Now here, I need to do what I need to do. Well, I guess I need to say that raw arguments storage is oh, we need allocator. That's fine. We can pass one. Okay. We also need to put it in the header. I guess, maybe. Maybe not. Okay, let's just put it here. So allocator, I think we have. That shouldn't be a problem. Function info. That might be slightly a problem. Wait, how does this work again? Define arithmetic, define compile time function. Right. Okay, so yeah, that's fine. Here we can say raw arguments I descriptor, that's gonna be I, and I, and then the last one, the mode, is call. And now I need to shuffle some things around because this needs to be here, but then it cannot have memory layout items. So that is going to be slightly well, here's what we're gonna do. We're gonna take this initialization and we're gonna put it in here. And then we would say descriptor memory layout items items. Storage is not a member of memory layout item. You are very right about that. Needs to be absolute. Memory layout is not a member of descriptor. Function info. I thought it was. Yeah. So it's descriptor function info. Function undeclared identifier. I think what you wanted is this. Okay. So it looks like that actually did work. And here we also can change now, because we can just say for index and then context allocator, descriptor function call. Yeah. Arc descriptor index. Right. That seems better, if that works. Two view arguments for a call. That's because I misspelled context. Arc value, yeah, we no longer want to push this. We actually want to push this stuff now. Okay, who's next? Right, that is that's an interesting question. It's about comparing functions. Should we compare them the same or not if they have the same names but they have the same different storage? So like imagine one has an argument in a register and another one has an argument in, I don't know, in on a stack. Like, are they still the same? Should we consider them the same? I don't know. But for now I will consider them the same, just so that we can make some progress and can get to compiling state in a second. Different const qualifiers. You don't need it to be non-const. Okay, well, that was a lot of changes. Let's see what's gonna happen now. I bet it's gonna be bad, but we'll see. Well, it's not as bad as I thought. We made it some duration, but it looks like we still have problems. So we are trying to get, we are here and we don't have a descriptor. That is very sus. Okay. Um, is this one of the tests that's supposed to be failing? Yeah, okay. I know what the problem is. Problem is here. We need to early out. I don't think we need this thing now. Wait, maybe we still may want this comment. Okay, let's try this again. And amazingly, I think all the tests are still passing after the refactoring. That is great. I think I will commit this. So it's episode 160, and we are saying that replace function argument with memory layout. Okay, that is great. Now, probably to drive the point home, we can try to make the change in the struct, and that's gonna be another very interesting journey, because there are some assumptions in the structs about how they work, which might cause problems. But I mean, the whole point of this video was to show that we can use sort of the same concept in both places. Well, it's time to put my money where my mouth is and actually implement that. So struct fields, not a thing. Struct here is also not a thing, I guess. Instead, we would have memory layout. I want to still call it struct. I guess I still want to call it struct. And then I would say here memory layout. Okay, well, the same stuff. We have lots of errors. Uh, items, descriptor. So it says I have an infinite struct. I'm not sure why that is the case. Okay, what if we just... no, that does not help in the slightest. Um, that's kind of interesting. Fields is not a member of descriptor struct. Where does this start? Mm, yeah, okay, I know what the problem is. That is coming from this macro where I had a struct and had a name. Okay, name is no longer a thing. Actually, no, it is here, but here we would say memory layout and interesting. Okay, dynamic array internal of descriptor fields. Okay, that is fine. The memory layout item. So something like that. Well, I guess that is improving, but not much. Okay, so there is an offset and we need to change how that works. So when we generate these things, they have an offset, but it should be, instead of just offset, it should be base relative, relative offset. And I also need to say that the tag is memory layout item tag base relative, and I don't need a name here. Left of items must have struct union type. What is not struct union about it? Ah, yeah, okay. That's because I thought I needed um, to put this into a pointer, which I don't need. Okay, the generated types are fine. Now all there is to do is clean up all the other stuff, which is fun, fun, fun. Okay. Items. We get field. For now, we will assert here that field tag is base relative, and we will get offset from the base relative. I mean, technically, this should happen once at the moment of creation rather than every time I try to call struct by size. So fix me, do padding when memory layout is created. But that is a separate topic. Okay. That is something we can fix. Easy. And then we have a pretty easy thing to just mostly renaming stuff. Now, here is where things are gonna get interesting. We would just say that tag is tag base relative and base relative offset is offset. This is a comparison function. Okay, we have field A, field B. Storage. Well, okay. If a field tag is not B, field tag, then it's they're not equal. Okay, not equal here. If they are equal, we need to switch on a field tag. And there are two options. One is base relative. Okay, then so here basically I just need to say base relative, and if it's case absolute, then I'm just gonna panic and say I have no idea what you're talking about. To do. Okay, that takes care of this file. Interestingly, nothing in here, nothing here, nothing here. And we have a bunch of stuff happening in here. Okay. And this is where you start to see sort of unifying. Previously we have this storage field access, but now we would have memory layout item. Oh, right. And I think here those will also will be replaced by memory layout. For now, I will just not gonna do just the type renaming, not anything else. Okay, this is pretty boring renaming, but you have to do it. I think I will replace, do this global replacement. That just should help a bit. Okay, getting there. This is not fields, this is that. Okay, what's happening here? Right. And then we need to say that field tag is so all of that will eventually be cleaned up. But for now, it's all gonna be just asserted. Okay, we'll see how we are doing and go from there. Let's try to run tests. Okay, so that was just mostly a name refactoring, but it brings me one step closer to where I want to be. And now we can actually I can start to go through all of this code very slowly, methodically, not in this video, and one by one look at these kind of asserts, right, that expect only a certain kind of layout to be available in a certain kind of place, and just slowly go them one by one and make sure that there is both branches. What if it is base relative? What is not base relative? And go from there. But I guess that will be it for today. I'm very excited about this development. Hopefully it works out well. If it doesn't, I'll let you know. And again, if you have any questions or suggestions, please leave a comment below and I will be happy to answer. That's all for today. Thank you very much for watching and hopefully see you next time.